We're going to be talking about ionic bonding and ions in this video. So in order to understand what happens in an ionic bond, we're going to draw out an ionic bond for the relationship between sodium and chlorine. And then we're going to do another element that bonds to two different things. Maybe we'll do something like calcium chloride. Okay, we'll do sodium chloride first, and then we'll look at what happens, how those two atoms come about bonding, and then we'll look at calcium chloride. So if we look at our two atoms of sodium and chlorine, okay, in actual fact, sodium is a larger atom than an atom of chlorine, because we know that as we move to the right of the periodic table along a period, atoms, even though they get heavier in terms of their atomic mass, they actually get smaller in size and more compact. Okay, that's why if you look at the vast majority of these images of these atoms, you will see that chlorine is actually a smaller sized atom, even though it has more. But what I want you to notice here are the little electrons, the X's. Okay? We know that sodium, which is in group 1, okay, Na is in group 1, which means it's going to have one extra electron. We also know that chlorine, which is in group 17, has 7 electrons, which means it's going to need one on its outermost shell. So when these two atoms are combined or they're mixed together, what ends up happening here is the actual electron from the sodium here gets cut off and it gets brought over to fill the actual outermost shell of chlorine. And in doing so, okay, while it does this, this outer shell of sodium ceases to exist. It's still drawn here, but it doesn't really exist anymore because there's nothing on it. So what ends up happening here is the sodium, okay, the sodium here is going to move over and is going to bond to the actual chlorine to create a molecule of sodium chloride. Okay, notice how we put the metal first and then the non-metal second, right? That's how we make these ionic bonding molecules. So this becomes a nice, awesome molecule. It's happy. It follows the idea that molecules are two or more atoms, whether they're from the same or different types of atoms. Awesome sauce. Okay, this is nice and neutral. Everyone's happy. Now, what ends up happening here, if for some reason this molecule dissociates. Dissociates means it breaks up. This is a couple, they're breaking up. Okay? Sodium goes its way, but look at that lone electron. Chlorine gets to keep sodium's stuff after they break up. Okay, so now, if we look at sodium, and we look at the number of protons versus the number of electrons, sodium still has 11 protons. They don't go anywhere. They're huge. They're lazy. The only things that move are the electrons. How many electrons does sodium have now? It only has 10. Okay, so it still has 11 protons, right? It still has 11 plus, but now it only has 10 minus. It only has 10 electrons. So this ion, it becomes an atom becomes an ion when it doesn't have the same number of protons as electrons. This ion now has a charge. It's got more positives than negatives. And we work this out, okay? We work this out by saying 11 plus, and then writing out our 10 minus is going to give us 1 plus. This ion will have a positive charge. So when we want to write this, okay, we end up writing Na1 plus, or Na just with a plus. Either or is acceptable. If we look at chlorine now, if we go up to chlorine, okay, and we move up here and we go to chlorine, we see that chlorine, after the breakup, now has sodium's old electron. It's not giving it back because chlorine is nice and stable. It's a happy camper. So how many electrons does chlorine have now? 18. It now has 18. So we look at this where we write up, same as we did over here, chlorine, okay, now it still has 17 protons, but it now has 18 electrons. So this ends up, when we add them together, it ends up giving it a 1 minus. It's got more negatives. It's got one more negative than it's got positives. So when we write this guy, we write Cl 1 minus, or Cl minus. We have just created, by breaking up something that bound together ionically, and it broke up, we created 2 ions. So just to go back here, okay, ionic bonding is when one atom gives an electron or one or more electrons to another atom. It cannot take them back. It's a full-on, I give it to you. Okay? It doesn't change its mind later and say, okay, I want those back. I don't want to hang out with you anymore. Once the giving takes place, it cannot be undone. Okay? So when we talk about ionic bonding has to happen in order for ions to be formed. Okay? When we talk about ionic bonding, we're talking about an atom giving away electrons to another atom in order for them to become a molecule, to make it nice and stable, so that both of the atoms in that bonding will have full valence shells. So let's look at something that is not just a one-to-one giving. Let's look at something like, something in group 2 with something in group 17. So if we look at the bonding of magnesium and fluorine, we're going to see that magnesium's got 2 valence electrons. How many valence electrons would fluorine have if it's in the halogen family? Group 7. It's going to have, group 17. It's going to have 7 valence electrons. So let's draw one of those. So here we have fluorine and magnesium, and we want to bind them together. Magnesium has 2 valence electrons. Fluorine has 7. So how many electrons does fluorine need to fill its shell? It needs 1. So it will take one of those actual electrons from magnesium. Okay? It will take them, and in so doing, it's going to bring that fluorine closer to the actual atom. So this is nice. That fluorine is so happy, it's stable. But what's wrong with this picture? There's still a valence electron left in magnesium's outermost shell. And that's not stable. So what has to happen here? we have to find another atom of fluorine to take up that second electron. Okay? So again, we're going to see here that this actual little electron, this last standing electron on magnesium, is going to be given to a second atom of fluorine. So we notice that in so doing, in giving that fluorine, another atom of fluorine, that last valence shell, that last valence electron on that outermost shell, magnesium now reverts back to its second shell, that it's totally full with 18. It's given away those two outermost electrons to each fluorine atom. So if we wanted to look at the charge of this, okay, magnesium has how many protons? It's got 12 protons. But now, if these guys break up, okay, so if these guys actually break up, if we take this guy over here and we move it back away, and then we take this guy over here, okay, this is probably going to be messy, but whatever, and we move it over here, poor magnesium is left with a loss of electrons. If we want to look at what kind of ion magnesium becomes, we say that it still has its 12 protons. The proton number never changes. How many electrons does magnesium now have? It only has 10 electrons, giving it a total of 2 extra protons. So magnesium as an ion in this case gets a 2+ charge because it's got 2 more protons than electrons. Same with the fluorine. I'm only going to write it out once. Okay, fluorine has 9 protons. How many electrons does it have now? It's got 10 electrons, giving it a 1 negative charge. So fluorine here becomes a 1 negative. And the same thing would happen over here to this guy. F, 1 negative. So this is where we see that an individual atom can give up more than just 1 electron. The 1-to-1 is nice because it's neat. It's quick, it's easy, it's painless. But it does happen that individual atoms can give up both of theirs. And it does happen that individual atoms can give up 2 or more electrons to one other atom. If I took something in group 2, okay, and I took something in group 6 that needs 2, that would be a 1-to-1 ratio. All right? Now, an easier way to do this than drawing out all of these rings and these colorful X's is using the Lewis notation for these atoms. And what I mean by that is if we go back to our NaCl, okay, we'll draw out the Lewis structures and we'll see how they can combine. So if we want to use the Lewis notation to show ionic bonding, all we've got to do is draw the Lewis structures for each of these, and we can show how when they come together, okay, chlorine is going to end up taking, and that's the reason that I've drawn these in different color, just to show you that if they form an ionic bond, chlorine is still taking that 1 electron. And if they should happen to split up, chlorine will go its separate way, and sodium will be left with no valence electrons. Well, it becomes an ion. Okay, this is just to show Lewis notation doesn't actually show the actual charge of things. It only shows the sharing of things.